Well, thanks a lot, Christian, for the introduction. So let me tell a bit about my history and how I started working with S2E. So back in 2008, I had a personal problem. So I had a 64-bit Windows laptop, and there were no drivers really at that time. So I wanted to reverse engineer existing drivers to port them automatically to my Windows 64-bit machine. And well, I did that like manually, like I was analyzing execution traces, looking at registry values, taking backward slices, and it was pretty tedious. And then we thought out, how do we make sure that we exhibit all the functionality on the device driver in an automated way? And then we came across a technique called Symbolic Execution. And right at that time, KLEE was being developed, and we were lucky in the lab to get access to the internal version. And then we combined it with QEMU, and that's essentially the ancestor of S2E. And so besides reverse engineering the drivers, we also thought, hey, how about finding bugs in device drivers? So we built a bug finder. And well, then we stopped for a minute and said, hey, how about we, since we can do all these applications with symbolic execution on a system level, how about we build a platform and have reverse engineering and device driver testing as like plugins and like different tools. And well, that's how we created S2E, and 1 year later we released it, released the first version to the public. And ever since then, I've been maintaining it, providing tech support, making sure it works, keeping up with like modern software. And in 2014, I graduated from PhD from the lab together with a few of my other colleagues. And we decided, well, how about we start a company? So how about we try to sell some of the tools we thought about to enterprises? So one of our ideas was to use S2E to scan documents for malware. I will talk about it more in the presentation. And right at the same time, there was like the DARPA Cyber Grant Challenge that came. And so we said to ourselves, hey, why not try it out? We have everything ready anyway, so it makes sense. And yeah, we managed to get to the finals. And well, since then, we released everything we did at the company to the public. It's like on our GitHub, you have everything there. And today what the startup is doing is like also inspired from like program analysis. Like instead of tracing data flows in programs, we do data flow tracing in enterprises. And we basically protect companies against insider threats, data leaks, and more generally, we provide visibility of all the data to enterprise security engineers. All right, so let's go into more details of S2E. So S2E is a platform for in vivo multipass analysis of software systems. What does this mean? Analysis means that you can write tools such as bug finding, verification, testing, security checks, etc., etc. Multipath means that we explore all the software behavior along multiple states, multiple executions. There are many techniques you can use to do multipath exploration. So S2E implements symbolic execution, concolic execution. There is also some preliminary support for state merging. It's a platform, so that means that it's extensible and you can write it for pretty much anything. We'll see later how other people used it. And it's in vivo. That means that you run your tests, your software in the actual system. There is no need for environment modeling or things like that. So you get more accurate results. And finally, it's like for software systems. So pretty much anything that runs on a CPU can be run inside S2E. So these are some of the few papers in the past 12 years that used S2E for all sorts of different things across different operating systems and different layers of the software stacks. You have, people have built tools for testing applications, libraries, kernel, even device firmware, and distributed systems, and all that across all sorts of operating systems. So this sort of shows that S2 is a fairly versatile platform and can work well for many applications. So here's the outline of this talk. So in the first part of the talk, we'll go more about the details of S2E, so how it's designed to provide all these feature functionality. And the second part will go into concrete use cases that we try to implement. So automated vulnerability analysis of the DARPA Cyberhaven challenge and scanning documents for malware. Spoiler alert, these two first ones, they failed. So, and today we don't use S2E for the third one. And then we'll see the future of S2E as how I see it. So there are many things I want to do with it, but based on some like all the feedback I get from people, is like, it still can be slow, and there are like low hanging fruits that we can easily pick to make it 10 to 100 times faster. So I will show you how to do that. All right, so let's start with how S2E works. So I will explain yet again what symbolic execution is to make sure that everyone understands. So, well, okay, so you have your function that takes symbolic input. And yeah, so you get path constraints, and eventually you call the constraint solver to get concrete examples. Okay, so this is what you would typically have in KLEE. So what's different in S2E is that instead of having a few bytes or kilobytes of state, you get the state of the whole computer, which is pretty much the CPU registers, memory, devices, hard disks. And that can be pretty big. So you are dealing with like tens of gigabytes of state. So of course we do like all sorts of optimizations, copy and write and things like that to make it tractable. But yeah, it still gets pretty expensive when you have to fork thousands of states in your program. So how did we architecture the system to make this possible? So here, so basically S2 is based on the QEMU virtual machine. That VM runs, well, anything that an x86 CPU can run. And so S2E is the emulation layer that's below that VM. So it's based on dynamic binary translation. So it looks at every instruction in the VM that's executed by the guest, and translates it to the either host CPU instruction, or if there are symbolic values manipulated, it will use the symbolic execution engine, which is currently implemented by KLEE. And below all this, you have the instrumentation engine, which gives the powerful ability of having plugins. So you have two types of plugins: the analysis plugins, so those like check properties on execution paths, like do we have, can I have a failed assertion? Can I have a security vulnerability? Can I have a crash? Something that you can encode as an assertion check. And you also have path selection plugins. So these like are responsible for selecting which parts of the program you want to explore, which path you want to keep, which one you want to kill, etc., etc. Yeah, and of course the search heuristics like depth first search, etc. All right, so this is at the theory level. So let's be now a bit more concrete. So the new architecture of S2E is like it's completely decoupled from the virtual machine. So QEMU and S2E are completely separate. So the way it works is that S2E lives inside the lib.s2e.so shared library, and it gets injected into the QEMU process and intercepts the /dev KVM interface. That essentially means that your VM thinks it runs on hardware, but actually behind the scenes, S2E intercepts all the KVM calls and does the symbolic execution in background. We did have to extend the KVM interface a little bit to accommodate for multiple states. Basically, we need to make sure that DMA accesses get written to the right memory pages. That's about it. And so the nice thing about this architecture is that you don't even have to use QEMU as your hypervisor. I mean, for example, we wrote PyKVM, which is like a tiny hypervisor written in Python, and you can use it like to check, like to run like small pieces of binary code, like when you don't need essentially the overhead of the whole QEMU VM. All right. So yeah, and the modular architecture, so I want to stress that a bit again. So we have like different components that are as standalone as possible. We have the dynamic binary translator, which we actually extracted from QEMU and made a library out of it. We have the symbolic execution engine, which is KLEE. I'll talk a bit more later how we actually improved KLEE for S2E purposes. Of course, we have the instrumentation engine, which is also a set of plugins with a defined interface. If you are interested, you can rip it out of S2E and put in your own symbolic executor if you want. And yeah, that's pretty much it. So let's now see a bit how dynamic binary translation works, which is like the heart of S2E. So it's not very complicated. So it's essentially an infinite loop that keeps fetching instructions at the current program counter, translates them to the host CPU instruction set, executes them, then gets the updated state, the program counter, and starts again. So here's an example of how a translated block of code would look like. So here you have an instruction that moves the contents of the EAX register into the memory location pointed to by EDX. And this is what happens when you translate. This is how it looks when it's translated. So this is the C pseudocode, like in real is like assembly instruction. So it will operate on a CPU register structure where the register values are stored, and then it will call various emulation helpers to actually execute some of the more complex operations. The translation process is split into two phases. There is a front end that converts the guest instruction set, for instance, x86, ARM, MIPS, RISC, whatever. It outputs then a set of like micro operations, and then translates in the backend these micro operations into actual host CPUs. And so this is how we instrument the code. So we insert S2E's instrumentations in this translation process. So on each instruction, we'll have a call that will ask any of the analysis plugins if they want to instrument that instructions. Basically, if they want to be called or notified when that instruction gets executed. And if one of the plugins says, yes, I want to be notified, it will return true here. And then the translator will emit a special micro operation that will instruct execution to the S2E later. And so this is how this generated code looks like. There is just a function call to S2E plugin, essentially. All right, and how do we support symbolic execution? Very easy, just add the backend for LLVM. So instead of translating instructions to native like host CPU instructions, we translate them to LLVM bitcode, which then can be easily interpreted by. And yeah, this is how it looks like. So you have the source, the guest instruction, and this is how it looks like in LLVM, and then it can be consumed by KLEE as is, more or less. All right, so let's see a bit more how we change KLEE and what are the improvements that we made. So we still use KLEE versions that we got like 2008, 2009. We stripped it down to the bare minimum, so we ripped out all the runtime, and basically we don't need any of that because like we only need to interpret LLVM instructions that are generated by QME, which are very restricted subset of what we typically find in general compiled software. Then we replaced STP with Z3. So in practice, we noticed that STP kept crashing for many of our use cases. So it was just easier to replace it. And it's much more reliable. Since 2008, we kept upgrading S2E to like newer versions of LLVM. So we cherry-picked upstream updates for LLVM. And yeah, we also added concolic execution support to KLEE. So let me show you how the concolic execution works. So that's the same example we had before. So if you run symbolic execution, you will get an execution tree. In most cases, the tree will be so large that path heuristics will get lost, and you won't make much progress in the execution. So concolic execution is nice in the sense that it will allow you to use like golden seeds in order to guide symbolic execution along the path that actually gets to terminate your program. And yeah, and basically we extended the KLEE with that. So we have an assignment cache essentially for each symbolic value. And when there is a if statement that forks, we know exactly which branch to follow because we can evaluate the concrete inputs. Note that this definition of concolic execution is a bit different from the original paper in Dart, which was running individual concrete runs, collecting constraints and negating things. All right. So further KLEE improvements that we made, those were very critical from like software engineering quality standpoint. So the first improvement we made was to make expressions immutable. So if you look now in KLEE, the expressions, they have like public methods that anyone can access. People can pass references around, and we run into serious issues where people would take references to these variables and then assign things to them, and then you end up with cycles in expressions, and you get all sorts of weird corruption. So we make them private and immutable, essentially. Yeah, so that eliminated a whole bunch of bugs for us. Then we also try to improve a bit the encapsulation. We noticed that, for instance, the executor class is extremely big and tends to access like public fields in all sorts of other classes. So we try to move the methods to the right classes. Like, for example, all these methods that take execution state as the first parameter, well, they probably belong in the execution state class in the first place because of that. Okay, then there are two more improvements. So we've been profiling S2E, like people complain about all sorts of memory leaks in there. So we improved the situation by using smart pointers almost everywhere. So there are no more new and delete, and memory management is sort of done automatically now. So that eliminated these issues. And finally, maybe a bit more technical for those who know the KLEE internal. So you have like memory object class and the object state class. We noticed that memory object carries a lot of metadata that's specific to LLVM programs. We didn't need that in S2E, so we cleaned that up, and we ended up with like a couple variables left. So we just merged the two classes. Again, after profiling, and that we noticed that we had lots of memory allocations, and so this sort of alleviated memory pressure on the execution. All right, so this concludes the first part of the talk. So now I will explain more like in practice how we try to build things with S2E. So the first sort of product we talk about is the automated vulnerability analysis tool. So it started always participating with the DARPA Cyber Grant Challenge. So for those who are not familiar with it, in this challenge we had to like automatically find vulnerabilities in software in order to attack all the competitors, and we also had to defend our software against attacks from others. And of course, doing that while keeping the software responsive and like doing the functionality. There were 7 teams in the finals. Interestingly, 2 of them actually used S2E. So there was Team Dissect and our team, Team Kojitsu, which was a collaboration between Cyberhaven, UC Berkeley, and Syracuse University. So let's see a bit about the results. So we were the fastest to find attacks together with Shellfish. And we had the second most effective system at attacking other competitors' systems. But despite this, we still placed only like 5th in the final results because we messed up the availability of our services. Remember that you had to both attack and defend while making sure that your systems are not down. And because of like some bugs in our implementation, we suffered here a little bit. Okay, so let's look a bit at the architecture of this system. So it's an extremely complex system that has many different components for attack and for defense, and they all communicate with each other, exchange information. So for attack, we have symbolic execution integrated with the fuzzing engine. So both of them were exchanging seeds in order to help each other finding vulnerabilities. And we combined that with traffic replay. So we were like sniffing other people's network communications, like to see, like try to reconstruct attacks and help us finding more vulnerabilities. In parallel, we had the defense layer. So that was about hardening program binaries. So we were trying to find the holes there and like adding extra bits of code to make them more robust and prevent them from being exploited. And for that, we needed a disassembler, static analysis, and like performance testing to make sure that we don't add too much overhead because we can be penalized for that. And of course, so all these things had to be integrated with the DARPA interface, which would send us challenge binaries. We would then pick them up, analyze them, create all like the required tasks in order to schedule all these analyses on the right. These tasks are stored in a database, which is then read by the task scheduler, and that scheduler will then execute what's needed. And once we get the analysis results, they are put in the database. The team interface reads them, and then sends proof of vulnerabilities and hardened binaries to the DARPA system. So that's a lot of components, and we had to like run them on a very large cluster. It was like phenomenal hardware specs for the time. 64 nodes, 20 cores, 256 gigabytes of memory, I think, for each node. I don't remember, and like yeah, pretty big disk. So we had to run all these tasks like with like highest possible reliability. If you crash in the middle of the challenge, you had no access to the machines to debug. So it had to run on its own very well. So for that, we used all the state-of-the-art at the time deployment tools like so database storage as Postgres, GlusterFS, Ansible for automated deployment, Docker, of course, to containerize all these applications, The scheduler was done by Mesos, and of course, like health monitoring, make sure you have proper recovery if something crashes. So you also have to have that there. All right, so this concludes the first application. So we released all the code for the exploit generation part. So you can find it on the S2E website. There is a demo that you can run with one line of code. And yeah. So this brings us to the second use case, which is about scanning documents for malware. So when we finished the PhD, we started Cyberhaven and we wondered, okay, what can we apply this technology for? So we looked a bit at what people are doing. So we thought, yeah, well, it's hard to sell S2E as a tool because, well, developers don't really pay for tools. They expect them to be free. So instead, we targeted enterprise customers and we tried to see what were the problems. And one of the problems that came up, yeah, we have problems with malware, we get attacks. Okay, let's try to build a malware scanner. So we selected a technology, a control flow integrity. We implemented that in S2E. We made it run on a bunch of software that were most commonly used by companies like Office documents, PDF readers, and across several operating systems. We implemented that in the cluster in order to be able to scan like millions of files. There are a lot of files that can come by email and all sorts of sources. Yeah, so that's what we did. So let's look a bit more in detail about control flow integrity checking and how we did that in S2E. So essentially, here, well, you have two functions, function and function one. So it's assembly code. You don't really need to understand what it does, but the idea is that if you have like a bug function that doesn't properly check its inputs, you might get issues like overwriting the return address of the function, and that allows attackers to hijack the control flow of your application and execute arbitrary code. And so here is what a typical stack would look in a normal run. In a run where the stack is overwritten by malicious payload, you will see that the return address here 10 is overwritten, and yeah, execution is hijacked. So control flow integrity checking will catch this thing using, for example, a shadow stack, which is a parallel stack that is maintained inside S2E and that's not accessible by the guest operating system. And that stack will record the valid return address when a co-insertion is called. And well, if there is a return here and it doesn't match, it will flag a CFI violation and you know that you have a malicious payload. All right, so we implemented that in S2E. So the CFI checker plugin is very small, like 600 lines of code. But it required a lot of support plugins around it. So you run into all sorts of practical issues, like you have to know where the system loads your process, where your modules are, when your process gets to be executed, where are your memory regions, and all that is outsourced to like independent S2E plugins. Then we had another practical problems with it, which is like handling all the stacks. So remember, we have like Office, Acrobat, Foxit, Windows XP 7, 8 at that time. So this like creates a combinatory or explosion of different OSs and apps. So we needed to implement an automated way to build these images. And this is actually open sourced as well. Now, when you install S2E, you can very easily generate images. You don't have to do it manually. It's very simple. And yeah, another thing we had to build. So when you are, this is an automated GUI clicker. So when you are testing Office applications, these are not command line apps. They rely on GUI, which is like event-driven architecture. That means that your app keeps running until someone clicks exit on it. And these apps can show all sorts of pop-ups that you have to somehow close. When you throw 1 million files at Office, you will see all sorts of weird issues like corrupted documents, which will show an error message. You will have, I don't know, Flash applications embedded in there. You will have videos. You will have all sorts of macros that show like warnings on the screen and that prevent execution from continuing until the window is closed. So we had to implement an automated clicker for that. There are obviously challenges. We had like fairly limited support of control flow integrity. We did not deal with self-modifying calls, self-modifying code. We didn't deal with jumps, and we had like issues like identifying like valid call targets. So it was very simple implementation. But nevertheless, it was enough to find some interesting things. So is some performance overview. So we scanned over 1 million files that were prospective customers. That resulted in 4 million analyses that average like 4 combinations of OS apps per analysis. And it was taking like 5 to 15 minutes to find the CFI violations. And of course, we had the timeout to shut down the analysis if we didn't find anything. So we found around 200 dangerous files. So these files were not detected by existing antiviruses. So yeah, so it was somewhat effective. But unfortunately, it wasn't interesting enough for the customers. So this product failed for a variety of reasons. First of all, it was too slow. Customers want to do inline scanning and remove malware right away. The coverage of that solution was fairly limited, so we only focused on documents. We didn't handle arbitrary malware like executables or macros or things like that. And the problem is that customers don't want to have yet another solution to manage. So they will still have needed to keep the existing antiviruses, and well, they just don't want it. It's expensive to manage and well, it creates problems. Also existing AVs, they deem them good enough, Symantec, I don't know, Windows Defender. And we also had like at that time, 2015, strong competition, like with solutions like Silence, which were like doing machine learning and were like so more like fun, so to speak, to deploy and use. And finally, yeah, too much time to demonstrate value. So you've seen the previous slide, we took like 1 million files and we found 200 of nuggets. So if you don't find anything, how do you convince a customer that your solution is working? Usually customers, they want like immediate proof of value. They install your thing, 5 minutes later, they say, yeah, I want that. Yeah, so that's what they want. Yes, and with this, let's move to our current offering, which actually works and sort of fulfills all these customer expectations. So now, after actually talking to customers, like doing all sorts of surveys, presenting them various problems and understanding what they want, we realized that, okay, instead of tracing data flows in applications with symbolic execution or whatever, let's trace data flows in enterprises. So in this diagram, you will see a typical workflow in a company. Like a user, Alison, downloads a report from some cloud service, compresses it to a zip file, sends the zip file by email to Jennifer and Charles. Charles opens the file, uploads it to G Drive, then someone else downloads that file, and some user somewhere uploads the file to WeChat, which is probably not what's needed. So what Cyberhaven does is that it builds these sort of data flows across the entire enterprise. So we have like billions of nodes in that graph, and that allows CISOs, security engineers to query it, and they can ask things like, okay, do I have any confidential information that gets sent to unsanctioned file sharing applications, for example? Do I have people who collaborate using private emails, for example? And to achieve that, so we have endpoint agents. So we install a lightweight agent on each computer in the enterprise. And that agent essentially records pairs of source and destination. So on this machine, it will record that there was a download from some website, and that download got saved in a file called files.zip. So you have first pair source destination. Then you have a second pair source destination, like which is attached the file to the email here that was sent to Charles. So once you do all this on each endpoint like sends all these pairs of source destination to the backend, and the backend aggregates all these edges across the whole company and produces this final graph. All right, so and this is what system security analysts will see on the dashboard. So they will see exactly what happens with the data in the company. So you'll see it here on the right, you have the configured data sets, which for instance contain like business data, content, sensitive content, IP, etc. So you can tag your data with different categories. And then on the right here, you have the destination. So you have mail sent to external email domains, documents that got printed, documents that got uploaded to social media, etc., etc., etc. Then you can see at a glance what's going on there. So we don't use S2E anymore, so that failed as a commercial product, unfortunately. Now it's open sourced. We had to build the technology from scratch after talking to customers and sort of go backwards from what customers wanted. And yeah, there are many new challenges like scalable data flow tracing. How do you handle billions of nodes and hundreds of thousands of endpoints? And yeah, we have like interesting, challenging implementation issues for the endpoints. How are you efficient to make sure not to crash your customers' machines? How you don't interfere with other security solutions, etc., etc. All right, so this brings us to the last part of the talk, which is what's the future of S2 essentially. So I said that the company wasn't using it anymore, so we released everything, and now I'm essentially the sole maintainer of it. And so there are many things I want to do with that. I hope it will be mostly driven by you guys, what you want, the functionality you want. Here, I wanted to address some of the low-hanging fruits, which is like, how do I make it much faster? 11 years ago, the experience using S2E was like that. So you download S2E, you try to install GuestOS manually, you try to boot it, you take a snapshot, you have to write a config file somehow. And like 2 weeks later, it still doesn't work. And yeah, so there was no documentation, everything was manual. So that is over. So now everything, all the tedious steps are automated. So you can get something running very quickly, depending how fast your machine is at compiling it. But yeah, it's still, once this runs and people start trying with their own programs, it's very slow. And okay, how do we make it faster? So there are two approaches for doing that. They are like orthogonal more or less. So like one of them is optimizing single path execution, and the other one is to optimize multi-path exploration. So I will talk here about the first one only in this talk. And yes, so let's go back to the architecture of S2E and see where the bottlenecks are. The first bottleneck is concrete execution. It uses the DBT, which is pretty slow, so about 10 times slower than native execution. It takes like 5 minutes to boot Windows 7 with that. The other source of slowdown is a symbolic interpreter. It's 100 to 1000x slower than native execution. It takes 1 minute to boot the BIOS, which it's a lot. And so what can we do about that? Let's look at this. So here the problem is that, well, DBT like blows up the number of instructions, like 10x more instructions essentially. And to fix that, okay, so we noticed that 99% of the code that runs in S2E is like, we don't have to instrument it, it doesn't touch symbolic data, so why do we even translate code? We just run it natively on like real hardware. And that's what we want to do. So essentially add an extra execution engine to S2E that will run all that code natively on the CPU so that you don't have needless slowdown there. Of course, it's very challenging to implement because then you have to figure out how to efficiently switch between KVM, DBT, KLEE, and well, then you have a lot of state to serialize, translate, and if it's too slow, it might actually negate the whole point of using hardware acceleration. And then finally, it's a bit tricky to instrument code that runs in KVM. So DBT has access to all the instructions, but once you run them into KVM, how do you abort execution if you see that you have an instruction that you want to instrument? So these are all the interfaces that you sort of have to think about before implementing that solution. All right. Next is how do we fix that? So this is the problem. We have two small instructions that get blown up to like this kind of LLVM bit code. Fortunately, so these are the problems first. So it's slow to generate. So just translating x86 code to LLVM takes, I don't know, forever. It's like 45 minutes to boot Windows XP if you do that. And then it's slow to interpret. So the pathological case is that you have a loop that zeroes out an array. It has 1 million iterations. And if you have to execute 1 million LLVM instructions times, I don't know, 100 instructions per basic block, you can spend the whole day doing that. So that's not acceptable. So we need an intermediate representation that is fast to generate and fast to interpret. Fortunately, QEMU comes with that. It's called TCI, Tiny Code Interpreter backend. So QEMU uses that when it has to run on an architecture that it does not support. And so the idea here is to extend it with a symbolic expression. So instead of using KLEE as an LLVM interpreter, we'll use that TCI. Well, we still need to use KLEE because so QEMU has this so-called emulation helpers, which are complex pieces of C code that get called when the translator doesn't know how to translate some particular instruction, or doesn't want to translate it because it's too complex and just easier to call the C code. So we'll still have KLEE to handle this case, and we'll have to switch between all these things. All right, so this is pretty much the conclusion of the talk. I'm happy to take your questions now.